Physics Penguin.
Hello and welcome to the second part of our work on moments. This week we will be identifying how levers work and the two types of lever that we use. Let's start by looking at the parts of a lever: the pivot or fulcrum, the force applied, and the thing that gets moved, which we call the load. The pivot is the part that everything else rotates around. The force applied is usually easy to spot too, since it's often where your hands would be. The load is the thing that is thrown or lifted or turned. This is a lever. A lever is something that gives us the ability to deliver a higher force than what you actually put in. A lot of tools are actually levers. Like we said last week, humans are not particularly impressive physically, but very early in your development, primitive humans started using levers. We used to think that only humans used tools, but creatures like chimps have been seen using simple tools, and some people have even argued that some groups of chimps have entered their own Stone Age by using stone tools and passing on the knowledge of how to do so. Anyway, let's see how levers might help a human. This human has to fight this monster. Without tools, the outcome is predictable. Ouch. But maybe the human can use a simple axe. When the arm swings an axe overhead, the shoulder is the pivot. The force for the swing comes from the muscles around the shoulder, close to the pivot. The applied force is at the point of impact. Well, that hurt. This weapon worked because the sharp edge moved a long way in a short time. In other words, it was fast. This is called a distance multiplier. The load moves much further than the applied force. This is possible if the applied force is close to the pivot compared to the load. The law of levers is that the applied force times the distance from the pivot equals the load times the distance from the pivot. In this case, because the applied force is applied at a close distance to the pivot, so this moment has to balance the load force at the very end of the lever. This only works if the load force is very small. Not convinced? Well, think about scissors. In scissors, the applied force is applied at the finger holes. The pivot is at the sort of centre of the scissors, and when you cut paper, the paper goes close to the pivot. This means that the load force will be very big. Let's work it out. Let's use an applied force of, say, 10 newtons. If the finger holes are 10 centimetres away, that's 0.1 metres. Now calculate the moment. Well, moment equals force times distance equals 10 times 0.1 equals 1 Newton metre. Now think about that paper. If the paper is 0.5 centimetres from the pivot, what will the force be? Well, the moment equals the force times the distance. So the 1 Newton metre we just found has to equal the force times 0.5 centimetres. 0.5 centimetres is 0.005 metres. So that means that 1 Newton meter equals the load force times 0.005. So the load will be 1 divided by 0.005, which is 200 newtons. This is 20 times bigger than the force we started with. So these scissors make you 20 times stronger. We call levers that make you stronger force multipliers. Levers that make a load move more are called distance multipliers. Let's have a look at some levers and see if they are distance or force multipliers. In each case, L equals load, F equals fulcrum, pivot, and E equals effort. If the effort is further from the fulcrum than the load, you have a force multiplier that makes you stronger. If the load is further from the pivot, then we have a distance multiplier that makes you able to increase the movement of the load. In these examples, the hammer is a force multiplier. It makes you able to pull nails out of a piece of wood. The wheelbarrow is also a force multiplier. It makes it possible to lift a heavy weight easily and move it around. The arm is a distance multiplier. The brick in the hand moves a lot, certainly more than the muscles in the arm anyway. The pliers and the nutcracker are both force multipliers, and the sugar tongs are distance multipliers. Just take a moment to check these. Let's think about balancing forces. When forces are acting around a pivot but nothing moves, then the total of the clockwise moments must balance the total of the anti-clockwise moments. All we need to do is calculate the moments and we can show that something like a seesaw will balance. Let's have a look at this example. If the walrus weighs 5,000 newtons and is placed 0.2 meters from the pivot, and let's say Ryan Reynolds is placed 1 meter from the pivot on the other side, what is Ryan Reynolds' weight, assuming it all balances? Well, the anti-clockwise moment is caused by the walrus, and that will be 5,000 newtons times 0.2 meters, which is 1,000 newton meters. Since the seesaw balances, we know that the clockwise moment must also be 1,000 newton meters. We also know that 1,000 newton meters equals the weight of Ryan Reynolds times 1 meter. 1,000 equals 1,000 times 1, so everyone's favourite Canadian must weigh 1,000 newtons. Sorry Ryan, I'm sure you're lighter than that really. Well, it's time for you to go and have a try at the questions on the worksheet I've put in the description. Pause the video and we will go over it all in a bit. Welcome back. Let's have a look at the questions. Question 1 is a sort of classic seesaw thing. We have an anti-clockwise moment of F times D equals 500 times 0.5 equals 250 Newton meters. Capital N, small m. The clockwise moment will be F times D equals 600 times 0.3, which is 180 Newton meters. This is what we scientists call less. So the seesaw will turn anti-clockwise, which makes the left side go down and the right side go up. Question 2. We need a moment of 10 Newton meters, but we have a force of 30 newtons and a maximum distance of 0.25 meters. So 30 times 0.25 equals 7.5 Newton meters. This is less than the needed moment, so nothing turns. If we wanted to make it turn, we could either use more force or get a longer lever. Question 3. It's a table question. Gotta love a table. In line 1, we have a moment on the right of 5 times 0.25 equals 1.25 Newton meters. So this means that the left side moment must equal 1.25 Newton meters. The moment equals force times distance, so force will be the moment divided by the distance, which for us is 1.25 divided by 0.1, which makes 12.5 newtons, so that's our missing number. In line 2, our moment will be 8.6 times 0.5, so that's 4.3 newton meters. So 4.3 newton meters equals force times distance, so distance will be the moment divided by the force. 4.3 divided by 7 equals 0.61 meters if I round it up. In line 3, our moment is 5 times 1.2, which is 6 newton meters. So the right side force will be 6 divided by 2, which is 3 newtons. Notice that we just divide the moment by either the force or the distance to get whatever is missing. In line 4, we've got 5 times 1.5 equals 7.5 newton meters. So the left side distance will be 7.5 divided by 6, which is 1.25 meters. And in line 5, the moment is 10 times 1.1, which is 11 newton meters. So the left hand force will be 11 divided by 3, which is 3 2/3, or 3.67 if you like decimals and don't mind rounding. In line 6, the moment is 3.5 times 2, which is 7 newton meters. So the right distance will be 7 divided by 7, which is 1 meter exactly. And that's how it's done. Well done for working through the sheet. Go back and check anything you're not sure about. That's about it for this week. So this is Physics Penguin on a seesaw saying ta-ta!